For most of human history, we have only ever seen one face of the moon. The near side hangs over Earth night after night, familiar in its dark basalt plains and pale highlands. It feels known, mapped, settled. The far side, by contrast, has always been hidden, locked away by the moon's rotation, permanently turned from view. For decades, scientists assumed that hidden face was simply more of the same. China's recent lunar missions have forced a fundamental rethinking of that assumption. In June 2024, China became the first nation to land a robotic spacecraft on the moon's far side and return samples to Earth. This was not a symbolic achievement. It was a technical and scientific breakthrough that has revealed the moon to be far more complex, more asymmetrical, and more resource-rich than previously understood. Landing on the far side of the moon is not merely difficult, it is uniquely hostile to communication. The moon is tidally locked, rotating at the same rate it orbits Earth. As a result, the far side never faces our planet. Radio signals cannot pass through solid rock, which means any spacecraft operating there is effectively cut off from direct control. For decades, this limitation alone prevented exploration. China solved the problem by launching a relay satellite into a stable gravitational position beyond the moon, known as a halo orbit. From this vantage point, the satellite acts as a communications bridge, relaying signals between Earth and the far side. With that infrastructure in place, the Chang'e 6 mission descended into the South Pole Aitken Basin, the largest and deepest impact crater on the moon. This basin is immense, roughly 2,500 kilometers wide and up to 8 kilometers deep. It was formed billions of years ago by an impact so violent it nearly fractured the moon's crust. Scientists have long suspected that this basin exposes materials from deep within the lunar interior. Until now, they had no way to test that hypothesis directly. Chang'e 6 landed autonomously, using onboard artificial intelligence to navigate terrain filled with boulders, steep slopes, and crater walls. For 15 minutes during descent, the spacecraft operated without human intervention. When it touched down successfully, it began drilling and collecting samples from a region no mission had ever accessed. 53 days later, a return capsule landed safely in Inner Mongolia, carrying nearly 2 kilograms of lunar material. What scientists found inside immediately challenged decades of assumptions. The first surprise was visual. Far-side lunar soil is noticeably lighter in color than the dark basalt plains visible on the near side. Those dark regions, known as Maria, are vast fields of ancient lava flows that erupted billions of years ago. The near side of the moon is dominated by them. The far side has almost none. This stark contrast, known as the lunar dichotomy, has been one of planetary science's most persistent mysteries. Why would one hemisphere be volcanically active for billions of years, while the other remained largely frozen and inert? The Chang'e 6 samples provided a clear answer. Chemical analysis revealed an extreme imbalance in radioactive elements known collectively as KREEP, potassium, rare earth elements, and phosphorus. These elements generate heat through radioactive decay. Apollo samples from the near side are rich in KREEP, explaining why that side of the moon remained hot enough for lava to erupt long after formation. The far side samples, by contrast, were almost completely devoid of KREEP. This confirms that the moon is internally lopsided. Early in its history, radioactive heat-producing elements concentrated on the near side, thinning the crust and sustaining volcanism. The far side, lacking that internal heat source, cooled rapidly. Its crust thickened, becoming too rigid for magma to break through. The moon, it turns out, is not a uniform world. It is two fundamentally different geological environments fused together. The chemistry grew even more unexpected. Under electron microscopes, researchers identified naturally occurring graphene flakes embedded in the lunar soil, sheets just 2 to 7 atoms thick. On Earth, graphene is considered a cutting-edge material. It is extraordinarily strong, highly conductive, and extremely difficult to produce, typically requiring advanced laboratories and controlled conditions. On the Moon, it appears to form naturally. With no atmosphere to slow incoming debris, the lunar surface is constantly bombarded by meteorites. Each impact generates extreme pressure and heat for a fraction of a second. That shock environment is sufficient to compress carbon atoms into perfectly ordered hexagonal sheets. Over billions of years, the Moon has functioned as a natural graphene factory. This discovery has immediate implications for future exploration. Graphene is ideal for lightweight structural materials, electronics, and radiation shielding. If it can be harvested directly from lunar soil, it dramatically reduces the need to transport construction materials from the samples, also provided the strongest evidence yet for the Moon's earliest and most violent chapter. Planetary scientists have long theorized that the Moon formed after a Mars-sized object, often called Theia, collided with early Earth around 4.5 billion years ago. The debris from that impact coalesced into a molten body, essentially a global ocean of magma floating in space. Until now, that idea rested largely on modeling. Chang'e 6 samples contain minerals such as anorthosite that could only have formed by floating to the surface of a molten lunar ocean. This confirms that the Moon was once entirely liquid. As it cooled, heavy minerals sank toward the interior, while lighter minerals rose to form the crust. The Moon did not simply assemble, it differentiated. Even more significant was where the samples came from. The South Pole Aitken impact excavated material from deep beneath the lunar crust, exposing portions of the mantle. On Earth, no drill has ever reached the mantle. On the Moon, an ancient impact did the work for us. The samples contain olivine and pyroxene, dense green minerals that belong far below the surface. Finding them in surface material offers the first direct glimpse into the interior of another planetary body. Scientists are no longer inferring the Moon's structure indirectly. They are holding pieces of it in their hands. Then came the discovery that may prove most transformative of all. For decades, the Moon was considered completely dry. Apollo astronauts returned with dust that appeared devoid of water. That assumption shaped every plan for lunar exploration. Water would have to be brought from Earth at enormous cost. China's samples shattered that belief. Researchers identified hydrated minerals, crystals with water molecules chemically bound inside them. This is not ice hidden in permanently shadowed craters. It is water locked inside rocks sitting in direct sunlight. Further analysis revealed that meteorites rich in water-bearing compounds have been striking the Moon for billions of years. With no atmosphere, no erosion, and no plate tectonics, that water remains trapped in the soil. Glass beads formed by micrometeorite impacts contain even more. When solar wind protons strike these beads, hydrogen bonds with oxygen to form water molecules stored within the glass. Estimates suggest that lunar soil could contain hundreds of billions of tons of extractable water. This fundamentally changes what the Moon represents. Water means life support. It means oxygen. It means rocket fuel. It means permanent human presence is no longer constrained by Earth-based supply chains. The samples also confirmed the presence of helium-3, a rare isotope deposited by the solar wind. On Earth, helium-3 is scarce. On the Moon, it has accumulated for billions of years. In theory, it could fuel future nuclear fusion reactors with minimal radioactive waste. China has been explicit about its interest in lunar resources. These missions are not purely academic. They are surveys, assessments of where water, construction materials, and energy sources exist. The geological timeline was revised as well. Apollo samples suggested lunar volcanism ended about 3 billion years ago. Chinese samples from the near side indicate activity continued until roughly 2 billion years ago. Far side samples are older, confirming that the far side cooled and died earlier, while the near side remained geologically alive for far longer. The moon spent nearly 1 billion years split between fire and ice. All of this feeds into a broader strategy. China has announced plans for an international lunar research station near the lunar South Pole by the 2030s. The region offers near-constant sunlight for solar power and deep shadowed areas where ice may still be concentrated. Other nations are watching closely. NASA's Artemis program is targeting many of the same locations. This is no longer a race to plant flags. It is a race to establish infrastructure. What China's Far Side mission ultimately revealed is not deception, but incompleteness. The moon was never lying to us. We were simply only seeing half of the story. It is a world born in fire, shaped by violence, divided by chemistry, and quietly storing the materials needed for humanity's next step outward. The far side is not a mirror of the near side. It is a different world entirely. And for the first time, we are beginning to understand it.